Welcome to All Things Policy, a daily podcast by the Takshashila Institution. We are a bunch of policy nerds based in Bengaluru, and we like bringing fresh perspectives to Indian affairs and Indian perspectives to global affairs. So grab a cup of coffee, sit back, and join us for today's chat.
Welcome to All Things Policy. I'm Aditya. On the 22nd of January 2026, a Falcon 9 rocket from the US company SpaceX launched 25 Starlink satellites into orbit. There are now more than 9,000 of these in orbit, and they are growing in sophistication. And Starlink is not the only one. There are others, including Amazon's Kuiper, which is now confusingly renamed LEO, as well as OneWeb and at least two major initiatives from China for megaconstellations of satellites. What does all of this mean? Most of these satellites are being launched into low Earth orbit, a few into medium Earth orbit. And even in low Earth orbit, most of these satellites occupy a narrow band somewhere around 500 kilometers above sea level. And in international affairs, possession is 9/10 of the law. This crowding in a specific narrow band of space that's really useful has profound consequences for the rest of us. It means that it's harder and more complex and more costly for other countries to launch satellites into these areas. It means that effectively some parts of space become the possessions of some countries. To discuss the extent of this problem, how we got here, and what some potential solutions are, I'm joined by Ashwin Prasad. Ashwin, welcome.
Thanks, Aditya. Great to be here.
Yeah. Can you just, for starters, put this into perspective? How does this business of crowding, or what you call orbital entrenchment, occur, and how does it fit into the the broader evolution of the use of space and sea and other geographies?
I always like to start at the beginning stages of a civilization of humans to think about why we behave the way we behave. And I think you could imagine a reality many hundreds and thousands of years ago where the area of control of a people was a village, and that's all they could defend, that's all they could control, because that's all they could surveil, and they could only ensure that small patch of land was theirs and nothing else was able to come and enter it or control it in any other way, or change ownership in any other way. But as many things improved, maybe it's the population, the resources available, or maybe the society itself changed. But one of the primary factors has always been technology. As technological advancements happened, this range has grown. And fast forward a few thousand years, and here we are with virtually all of the surface of the earth claimed by one nation state or the other. And there are still challenges for the places that are already claimed. We have border skirmishes with China ongoing in our country. We have the president of the US trying to claim Greenland. So there has always been this obsession, and also with a lot of good reasons, for humanity to try and control new geographical domains. The fact that the Indian Army has a few people stationed on top of the Siachen Glacier is also an effort to control certain domains, and for various political and security reasons. So as technology is advanced, we have been able to do this better and better. At some point, we started controlling the sea much better than we used to. Now we have territorial waters. We know that there is a possibly unidentified ship at any point that it enters the waters that we monitor using radars. We can communicate across large domains with antennas that are sophisticated enough. And it has also bled into airspace. We control airspace. We all have seen movies where someone flies a plane into some place that they're not supposed to, and there will suddenly be a fighter escort asking them to identify themselves, and with a notification that you have entered a certain airspace. So we have always tried to control these domains. And the domain that we have more recently tried to control to a certain extent, or the most recent domain that has seen human activity is the space domain. 1950s was when it started purposefully, with a few countries trying experiments that took them to space. But over the years, because of basic laws of physics and other technological limitations, no one has actually been able to control it in a way that denies that part of space to anybody else. And I see this satellite internet Megaconstellations as the first sign of this gradually changing. And it's been a very gradual shift. And it's not all of outer space, obviously, but it's a very specific part of outer space. In fact, the part that is closest to the Earth's surface, the closest to us sitting on the surface of the Earth, which is the lower Earth orbit. And the lower Earth orbit itself is also massive. It's 2,000 kilometers above the surface. But this narrow band of maybe 400 to 500 kilometers of orbits in the lower Earth orbit above the surface of the Earth is the place where these things have started to operate on a scale that is pretty new and pretty fascinating to study. And it has obviously happened only because there are very good economic reasons for it to exist, very good political reasons. But it is also, in a form, a contestation. And it is a race between countries. And we see this manifesting already.
Yeah, this is going to sound corny, but what you were speaking about, the expansion of human domains reminded me of the jump cut from 2001: A Space Odyssey, where a primitive weapon is flung into the air, and you jump cut to a weapon in orbit in space. But yes, so yeah, we get that. So obviously. The extent of human domains, or domains in which humans have operated, has expanded. And you mentioned land and sea, as well as airspace, and there are some, like you said, restrictions there. There is now national sovereign territory. Even at sea, there's a certain territorial waters. There are exclusive economic zones, and then there are international waters. And we have sovereign airspace, international airspace. But what's interesting about space is that, as a practical matter, if you're in any kind of reasonably stable orbit, it is a domain for everyone, and nobody in practice, at least in theory, owns it. And 20 years ago, this business of overcrowding or entrenchment would not have seemed like a problem. The 1967 Outer Space Treaty obviously did not see this at that time as a problem. Can you run us through what exactly has changed in the last 10 or 15 years? Because we're suddenly seeing a lot of these satellite internet constellations coming up. I understand there are plans for tens of thousands of more such satellites, all of them, or at least most of them, in low Earth orbit. So just run us through how this happened.
The Outer Space Treaty has been formed based on a foundation that was informed by the political and technological realities of the 20th century. And back then, it might have seen that the outer space as a domain is so vast that countries can operate in it without really stepping on each other's toes. There was obviously mechanisms to prevent a certain satellite from doing a certain thing based on its purpose. And so there were some anti-satellite technologies that have been developed. It can be a missile, it can be a laser, but those things did exist, but never in a sense where you prevent a whole country from accessing space altogether, because it didn't seem necessary. It seemed like it is so vast, and you can basically not control space, because nothing is stationary in space. Everything is dynamic. You launch a satellite, it has to stay in orbit. It cannot just exist in a certain place that you can squat on and continue to stay there. So the whole reality is very different. So when the Outer Space Treaty was formed, the foundation of the treaty became the fact that you should not claim sovereignty over outer space. So you don't go to the moon and say it's yours. Don't put a satellite in the orbit and say the whole orbit is yours. But also that no one would stop anyone else from using space. So it's free to use, but not to claim. And that has led the philosophy of space technology growing over the years. And we had a reasonable number of satellites being launched. Commercial operations have grown. More civilian technologies use space as an infrastructure that supports their backend. So satellites have grown in numbers. And what is interesting is that the rockets that were launched to carry these satellites to orbit have largely remained the same since the 1960s. The rockets still are liquid or solid fuel rockets. They still have the same kind of payload fairing. They broadly follow the same design architecture. But what is interesting is that with advancements in semiconductors and sensors and our ability to process large amounts of data in a small chip, we started to gain the ability to design control systems for these machines in a much more sophisticated manner. So over the last 10-15 years, a lot of companies started doing this, and a few predominantly do it very well today, which is that they used these control systems to save some of the fuel that the rockets carried. And the rockets would typically have a certain amount of fuel. They would fly off the surface of the Earth. They would place the satellites or whatever payload they were carrying in orbit or on another celestial body, and they would just burn up in the orbit itself. They were designed to be a one-time use device, the instrument that is used once and not again. And that has started to change now, because we now design rockets that save some of the fuel to make a return journey back to their point of launch. And they're able to fire off their thrusters in a way that the rockets can slow down their fall and eventually be recovered and be refueled, and after some routine maintenance, be reused. So typically rockets have become reusable. And with that change, many other economic and temporal factors change. One is it's a lot cheaper to launch now. It's not that the reason you don't hesitate to use your car every day is because you can keep using it. And it lasts for a many number of years. The same is on a primitive level true for rockets. You can continue to use a rocket many times for launch. So the cost of a single launch falls dramatically. You have to build a rocket, but it lasts for a few launches. And the only real expenditure is the fuel and some maintenance. It started off being partially reusable, that some of the rocket was recovered, and now whole rockets are being recovered, especially by SpaceX. They have gained such mastery over this technology that the rocket comes back and stands on the spaceport just as it was launched, ready to be launched again in theoretically a few hours if everything goes well. So with this, the cadence of launches skyrocketed.
Yeah, so I mean, just to give some perspective to our listeners, SpaceX had 165 launches last year. They'll probably have more than 200 this year. We're recording this on the 23rd of January. They've already launched 9 times. And a lot of these are these Falcon 9s, which are their workhorse, reusable rockets. So like you said, the rockets land back erect, and it requires a few hours of refurbishment, a few changes and all that. And they're ready, in theory at least, to go back into orbit. But so SpaceX absolutely dominates this, right? More than any other country. And what's interesting is that they don't just dominate launch. It's a vertically integrated company. So you mentioned that in your paper that something like 60% of active satellites in the world are Starlink satellites. So they have that basically, they have the demand as well, right? So to just tell us how that works and what they're planning to do with Starlink.
In a boardroom somewhere in SpaceX, the question that they'll have asked themselves is, okay, we have these cheap rockets and we can afford to fly them often. We can afford to fly them for very cheap without having to pay a lot of money. What do we do with this? And there is obviously a lot of demand for the rockets and for launch from around the world. But you're still then catering to the timelines of others, and considering the level of reusability that they had, and you put the numbers into context, 9 launches in the first 20 days of this year. For a country like India, which has many other rockets, but none of them reusable, we typically, those 9 to 10 launches is what we do in a whole year. So they're able to do this at a crazier scale than we have ever seen before. And they would want to use this advantage to put it to good use and be the market maker for themselves, so that they create demand and they take advantage of this technology that they have. And they did this using a vertical integration of sorts with their technology. They identified that internet is something that can be provisioned from space in a different way compared to before. This is not a new idea. Internet has always been there has always been efforts to communicate from space before, but that happened differently because that happened with launch being a bottleneck. So countries and corporations typically launched a few satellites, and because the satellites were very few, they had to be far away from Earth so that they could cover more of the Earth. You can imagine it as a torchlight that keeps expanding outwards as the light passes. So to cover more of the footprint of the Earth, they had to be further away. And so this launch as a bottleneck dominated a lot of the design. And so most of the communication satellites were placed as far away as 36,000 kilometers from Earth, just so that they could have enough coverage and provide communication. But what this did was that the internet that they provided was not consumer grade. And considering how pervasive and how essential internet has become to today's world, even at a consumer level, we want to do video calls, we want to stream Netflix movies, we want to game in real time with our friends from around the world. All of these things need very high speed internet, and internet that has very low latency. You should be able to transmit your voice or your data and have the other person hear it nearly immediately, nearly instantaneously. This requires low latency, which means the signal shouldn't be traveling through thousands and thousands of kilometers, and it should actually have a shorter path so that even at the speed of light, the perception of this data transfer is almost instantaneous. And so SpaceX figured they could actually do this. They can afford to no longer treat launch as a bottleneck. They can actually launch a lot of satellites, and they can actually provide an internet service which is very fast, which has a high bandwidth and has a low latency. And the best place to do all of this from was the lower Earth orbit, which is a lot closer to the Earth. And they chose these slots between 450 to 550 kilometers for their satellites. They keep diversifying this. There are a few satellites further down now, but basically below 600 kilometers in the lower Earth orbit is where they found the sweet spot for a low latency, a high bandwidth satellite network, which kind of acts as a mesh, because each of these satellites only covers as large as a city in their range. So they have to act as a mesh that talk to each other and kind of transmit data through the sky and provide coverage throughout the surface of the Earth. They started small. They started with the mid latitudes and eventually expanded, and they now cover all the major populated areas on Earth. And they figured that this was a great application for their own reusable launch technology advantage. So they just figured out how to manufacture satellites very fast, how to load a lot of these satellites in a single launch and send it up in a single rocket, and how to do this very quickly. And they figured out the software, they figured out the antenna technologies, which have evolved over the years, but they have still done that well. And now they have a use case for their own launch, which is that they keep launching satellites to the lower Earth orbit. These satellites then act as kind of a network tower that provides internet to the users on the ground. And it has become a global technology.
I mean, just to put perspective on this. So firstly, you mentioned we imagine that boardroom meeting, right? I mean, the thing that would strike the board members would simply be that with launch, you have a predictable revenue stream, but there's very little value add you can do to that. So you want some sort of end user product which you can charge people. So now, in the old days, this would have been, like you mentioned, in geostationary orbit, something like 36,000 kilometers above sea level. And because satellites move roughly the same speed as the Earth's rotation there, it basically covers a specific geography, a stationary geography. When you come to low Earth orbit, the satellites are moving much faster. And that's one reason you need this massive mesh of satellites. And the reason that you want to come lower is, like you mentioned, low latency. So really that means, for example, it becomes easier to stream something on your phone using Starlink than, say, some of the more traditional communication systems that are higher up in orbit. Not all satellite internet constellations use low Earth orbit, of course, because there's a trade-off, right, between coverage and speed. But since most of these satellites are likely to be concentrated in low Earth orbit, including the new Megaconstellations from China, can you give us a sense of what this means physically? I mean, are satellites jostling against each other? Or what exactly are the problems that you have when you have suddenly tens of thousands of new satellites in this narrow band of space?
The changes from this emergent phenomenon are very apparent, though it's not widely studied or talked about. To put the numbers in perspective, we have maybe 14,000 satellites, active satellites right now, orbiting the Earth above us. And 90% of these satellites are in the lower Earth orbit. So, lower Earth orbit is the smallest slice of outer space that we can operate in, and it also happens to be the most crowded, predominantly the main one that is the location for all space activity. And so 90% of these all satellites are in the lower Earth orbit. 70% of all satellites are internet mega constellations. Things like Starlink, OneWeb, Kuiper, which is now LEO, Guowang, and all the other satellite internet companies have set up mega constellations, and they account for 70%. And 60% of all satellites are Starlink. So Starlink is clearly a dominant player here. Starlink has over 9,000 satellites in the lower Earth orbit already, and they plan to expand it to over 40,000 later. And they are the ones that have made the most progress. So all the other operators are still in their initial stages of deployment. They're all near 1, 2, 3% of their targets. Many have filed for a lot of satellites and have not launched a single satellite, but assuming that they do, we're going to have even more satellites in the lower Earth orbit. And so when you have such a large number of satellites in a single specific part of Earth orbit, it is going to cause issues of congestion. And this congestion can materialize in two ways. And both are actually very related to each other. The first thing is that the physical problem of all these satellites themselves, that there is a physical aspect to these satellites. They're moving around in extremely high speeds, and it is not that these satellites in orbit can be envisioned as cars on a crowded freeway. It's not that these cars are jostling around, honking at each other and trying to outmaneuver each other in the orbit. It is more that these satellites are basically like autonomous driverless vehicles zooming past the sky at insane speeds, and most of the time they don't even see anybody else. It's just vast in emptiness, because remember, space is extremely vast, but because all of it is happening at such blinding speeds, when a possible collision does seem like it is possible, like there are two satellites moving at each other, the avoidance of that collision becomes a very high stakes game. They have to avoid that collision, and they'll have a matter of minutes or seconds to avoid that collision. And that is just two satellites. But imagine this happening between thousands of these satellites operating in the similar domain. You have, a serious risk of a catastrophic event, because if one collision can trigger more, it's like a chain, it's like an oil spill, it's like a chain reaction. It can make things worse once things start to go wrong. So when thinking about the problem of this physical space, there are ideas about carrying capacity. How many satellites can the lower Earth orbit, the LEO, really carry? And the estimates are very varied. So there is a theoretical high level estimate by MIT which says it can be as much as 12 million. There is also more, but this assumes extremely ideal operating conditions. That all satellites are being responsibly operated from the ground. As soon as the satellite's life is over, they're being disposed of or moved away from the orbit. And all of these conditions. More realistic estimates that consider the real operating conditions that we have right now, they range between 100,000, 175,000 satellites. So like I said, a lot of the satellites are still in their initial deployment stages, these mega constellations. So assuming that just the mega constellations that have started launching already continue to launch. And they have an obligation under the ITU, which we can get to later, that they have to launch 10% of their planned satellite numbers in 2 years, 50% in 5 years, and 100% in 7 years. So even if you give them 10 years to meet their numbers, and you assume that it's going to happen by 2035, we are looking at around 80 to 100,000 megaconstellations, satellites in megaconstellations in the next 10 years.
So what's the evidence that we have that it's already getting more crowded? Are there more collision avoidance maneuvers?
Yes, the number of collision avoidance maneuvers have skyrocketed. So because the carrying capacity is limited and we are dealing with a more crowded environment, there are some reports that back in 2023, and these are just Starlink, by the way, Starlink conducted around 25,000 collision avoidance maneuvers. So Starlink, with its high number of satellites, alone had to perform 25,000 collisions avoidance maneuvers, and this was in the first half of 2023. Okay, so fast forward to 2025, just the first half of 2025, 6 months, that number has grown to 144,000. So that's a lot more collision avoidance maneuvers being performed just by Starlink satellites in the low Earth orbit. And so the domain is getting extremely congested in terms of safe operating conditions. So if you leave carrying capacity out of the picture, because it operates on a lot of assumptions, and it's better for a parking lot or a road rather than the lower Earth orbit. If you start to think about this in terms of how bad can things get if something goes wrong, if you take that as a metric. There's been a paper that has been written about this, and they have devised a metric which measures how quickly things can go bad. And the assumption is that right now, everyone is monitoring their satellites and trying to be responsible and coordinate with everybody. So it is not a passive system where things are happening on their own. It's an actively managed system to avoid catastrophe. So if you assume that completely stops, that no one does anything, and things are just let satellites just orbit on their, keep orbiting, they keep moving, and what will happen then? How long will things stay safe? If you measure that, the numbers are very telling. So before this era of megaconstellations, back in 2018, you could theoretically have all the satellite operators around the world in the low Earth orbit just take a holiday and not come back to work and just let things go, and nothing would happen. I mean, there would be no catastrophe for 121 days. So it took 121 days of like lack of management for things to really start to go bad. But now that period has come down to 2.8 days. Which is basically nothing. Everyone needs to constantly be alert and manage this, because if you stop, it's going to go crazy. It's going to be a catastrophe that cannot be recovered from. And studies show that in the lower Earth orbit, specifically the crowded parts of the lower Earth orbit, a single collision can trigger a catastrophic event, a kind of event that we would not want to ever happen.
Yeah, I mean, it's saying something that 2018 are the good old days, right? But so I'm just wondering how this can be mitigated, right? So firstly, satellites are, when you say moving really fast, relative to Earth at that altitude, they're moving something like 7 kilometers per second. But those relative velocities may increase or decrease depending on between two objects, right? So typically, when a space object is about to hit you, you'd not actually see it, contrary to what we see in the movie Gravity. It would actually be that fast and would actually be that catastrophic. The other problem there is simply that our information about what is where in space exactly at any point of time is imperfect. It's space situational awareness. So presumably the challenge for the space traffic cops will become easier once they know what's where at what time, right? So potentially that could help maybe reduce the number of collision avoidance maneuvers, because in some cases you might be able to make the determination, well, it's a close call, but you'll be fine. Yeah. But, some of these are being done out of abundant caution for good reason, right? What are some other potential solutions for this? And I don't mean big solutions. We'll get to that in the end. But like just managing this at the moment, are there any other solutions on the horizon?
there are some market solutions that are emerging already. There are services that are offering better and better space situational awareness for the satellite operators so that they can be more safe and responsible in their operations. There is the bubbles of where the satellite is being positioned are getting narrower with increasing accuracy. But at the end of the day, it all comes down to coordination. Right now, the coordination is completely decentralized. Every satellite operator has to talk to every other satellite operator and make sure that they're on the same page in terms of how they're going to deal with potential collisions. So if you start to recognize that based on your data, you're going to collide with another country's satellite in a few hours or minutes, you have to literally call them up and coordinate and make sure that you don't both maneuver into each other in trying to avoid this collision, and make sure that you both responsibly create distance between yourselves, between the satellites, so that they can just zoom past each other harmlessly. And that is happening at a decentralized level. There is no official information channel where it is happening. You sometimes have the US military flag out potential collisions. There was this case last year that a Starlink satellite and an ESA satellite were about to collide. And the Starlink satellite was not aware of this because they had a malfunction in their system. And ESA satellite had to just do a unscheduled maneuver to move out of the way. And the problem is that this is a house of cards. You have one guy doing an unscheduled maneuver. You don't know what else it's going to change. And the system is so dynamic that it's not just that these things are the only events here. It's the perfect control. If perfect control would be theoretically possible if everyone spoke to each other and everybody was always on high alert, but there are some external events that you have to throw into the mix as well. Back in 2024, there was the Gannon geomagnetic storm, which caused atmospheric density to spike. And suddenly the air was higher and it was causing a different measurement of drag on these satellites. And basically, half of all satellites in the lower Earth orbit had to maneuver to stay in orbit. And so you have these systems where the entropy suddenly increases. How do you make sure that these events can come and go while the orbits remain safe? We can't keep doing what we are doing right now. It's a band-aid on a gunshot wound. You cannot keep having this system continue and be okay. So it comes down to coordination, communication, and management. Right now it's decentralized, but a centralization of this is a good starting point in some way. And it's also about better information, better technologies. Can you remove debris from the lower Earth orbit so that the crash clock that we spoke about, which is 2.8 days, can possibly move to 5 or 6 days, just so that you make the environment more safer? Can you have your own satellite be disposed of very quickly after its mission instead of having it just staying in orbit? Can you do that? It comes down to those.
Okay. So I understand this. So, and we'll come to the governance issues because you have some ideas there. But I want to first ask you about frequency. Starlink plans to have some 40,000 satellites in that constellation. Could that be 20,000 in the future? Because these satellites are increasing in sophistication. There are inter-satellite links and so on. What's the situation there? Are there technical solutions really, is what I'm asking.
So the physical lack of satellite space is one issue. The fact that there are so many satellites means it's much more complex to add another satellite to the mix, because each of these satellites is basically, it comes with a keep out volume and you can't occupy that volume with your satellite. You have to veer around it, and there are senior rights, so you have to make sure that your satellite is not causing trouble to all the other satellites. So it's the sophistication level of launching and operating a satellite has gone up a lot, so much so that many countries are automatically going to get excluded in taking part in this part of the space technology and economy, simply because they don't have the requisite technology or the capability to do it. So there is already a level of these dominant players occupying the physical space in the orbit and keeping others out, and effectively controlling this domain and using it for their own advantages and purposes. But the frequency aspect is where you start to see a more overt denial of these orbits to other countries and corporations. The idea with the frequency resources is that it should be completely exclusive. You can think of, so the satellites are up there to transmit data back to Earth or to absorb data that is being sent from Earth. And that is happening through radio frequency signals that are traveling through the atmosphere to your devices and back to the satellite through the atmosphere again. And the way these waves work is that they can't crisscross, they can't intersect with each other. If they do, then it leads to information loss. It is the waves, literally the waves are just made up of energy. So when you have destructive interference of these energies, you start to lose the data that they carry and they become useless. And that's why we have spectrum auctions for 5G, 4G in the country. That's why we have a lot of exclusivity mechanisms for the way these frequencies continue to work in our world. And there is an international regulatory body that coordinates this so that countries can work with each other in making this possible. So with the lower Earth orbit, because we are dealing with some rule of physics limitations here. One is the latency. We need low latency for it to be commercially and operationally viable. It needs to be high bandwidth because otherwise you're not going to be able to send a lot of data and information through this network. Combination of the factors means that you have to use certain frequencies in your satellite to transmit this data back to the ground. And these are specifically the Ku and the Ka band of frequencies. These correspond to certain frequency ranges in the radio frequency spectrum, which are most suited for this purpose. They can carry enough data, but they're also immune to some of the atmospheric losses that occur due to clouds and water vapor and dust and all of that. And it can travel this range of atmosphere, the distance between the satellite and the user, in an effective manner. So because of the international system and because there is no overarching authority, the coordination is just a first come, first served system right now. You want to launch a satellite and you want to use a certain frequency, you make a filing with the ITU and say, I want to use this frequency, I'm going to do it from here. The only expectation from you is that you don't bother the people that have come before you. And so the senior rights are to be respected. You make sure that your satellite and whatever plan you have for your satellite does not interfere with any of the plans that everyone else before you who have come have for their satellites, and you play nice with them and you do your own thing. The problem is that every new satellite has to deal with n+1 number of satellites before it in this coordination. And because the numbers have so rapidly increased, the number of filings have increased by 5.5 times in the last few years. In recent years, in a very short period of time, there was filings made for 1 million satellites in total, which is far higher than what we can actually sustain. So in this system, you basically are running out of these frequency lanes that have to be exclusive. So imagine a highway from Earth to space that only you can use, because that's the only way you're going to transmit data successfully. These highways are being used up. There aren't enough highways for everybody, and so whoever goes there first gets the highway. So Starlink has gotten a lot of the highways. Even American corporations that are trying to enter the satellite internet market after Starlink with the requisite technological mastery cannot do it the way they would have wanted to do it, simply because Starlink already has all of these highways for itself. So what about countries that start to want to do this 5 years later, 10 years later? Space is nobody's domain. It's, like we said, it's owned by all humankind. And that means that all humankind should be able to access and enjoy the benefits of space. But if you're going to create these conditions where very few countries and corporations have cornered all the frequency resources and all the physical resources in these orbits for themselves, how are we going to think about the future? What about India? What about when India wants to launch a satellite constellation of its own? These are extremely tough questions that we need to ask and start trying to find the answers for.
Yeah, that's sobering. I mean, again, for perspective, India might want to launch a satellite internet constellation, not just for commercial reasons, but also for strategic reasons. So, there are serious downsides to this. You mentioned the ITU. So from what I understand, the regulatory architecture for these satellites is, there's the domestic architecture, domestic law in every country. There's the Outer Space Treaty and the allied treaties. And then finally, there's the ITU. And the ITU is obviously limited in what it can do, right? So what are some of the important things that it can't do? Can you just quickly run us through that?
So ITU is a regulatory body, yes, but it is in many ways toothless. It is a body for coordination, and it is a body that says, wait and do this before you go, rather than saying, no, you can't do this. So it just has a number of regulations that countries need to follow for the sake of everybody, and as long as you do them, you can continue doing whatever you want to do. And it is born out of necessity. It is one of those rare international bodies that has full memberships across the countries of the world, because the countries of the world have to use it if they are ever going to use any communication using radio frequencies. And so it is also in charge of coordinating frequency use and orbits between countries, because the orbit or the physical space you choose for the satellite and the frequency use, like I said, it's linked to the distance and the atmosphere. So they're both kind of the two sides of the same coin. So the ITU is it coordinates between all the countries of the world and facilitates RF signal cooperation in order to avoid interference. So it has set a few rules for this, but it is not a body that says, no, you have launched too many satellites already, you cannot launch more satellites. It cannot go and tell Starlink, you've already launched 9,000, you can't launch more, because we need to reserve some satellite slots for other countries. It never does that. And that's again emerging from the principles of the Outer Space Treaty, where since you can't claim sovereignty, you can also not stop others from doing whatever they want to do. And so ITU is the reason everything still works is thanks to the regulations and the ground rules that the ITU has set up. But ITU is also not this body that thinks about humanity's visions for the future, or equity for all countries, though it is in its mandate. It cannot implement or enforce any form of equity or fairness when it comes to the usage of space resources.
Yeah, I mean, so just for perspective, again, the ITU started off as the International Telegraph Union in 1865. It was renamed the Telecommunications Union in the 20th century, and it's now supposed to regulate satellite internet. And it's constrained not just by its own institutional history and past, but also by the Outer Space Treaty, like you mentioned. So this sounds, Ashwin, like a conundrum out of which there are no solutions. So we'll have to obviously think deeply about this, and some big changes will be required. What are those big changes?
When I've thought about the solutions for the problems that we have spoken so far, I realized I could think about the solutions in terms of what we can do after the satellite is launched. So all these satellites, all these thousands of satellites have been launched. What can we do in space to kind of solve this problem? And I realized that there are a lot of solutions there that are worth thinking about. But just for the sake of paper that I've written, I thought it is better that I compartmentalize these solutions and think about what solutions can we bring about before the launch is made. So changing the system rather than solving the crisis, so that if the system changes, the ingredients that go into the system change, and so we will start moving towards a more sustainable form of space activity and exploration in the coming years. I definitely think there is a lot of solutions that we can get into in the larger scheme of things in terms of what we can do after launch. So space situational awareness, debris control, traffic management, better communication and coordination systems, all of that. But I don't want to get into those in this paper. So in terms of what we can do to change the system that allows for this problem, one of the ideas I have is that we can possibly charge a rent to the satellites that are operating in space and occupying this space in the low Earth orbit, because right now it's free of charge, and so none of the operators are optimizing for the number of satellites that they have to launch. In fact, that is the variable that they are most incentivized to drive to the fullest, because they can make cheap and small satellites that they can launch in huge numbers and provide redundancy that helps not just them but also their countries, because those countries now own those slots for the satellites and dominate the orbit while denying it to others. So if you bring in a price mechanism in there and make it hurt in terms of costs by bringing in an element that punishes this behavior of launching numerous satellites and not ever optimizing for that number, then you possibly have a change in equation where satellite operators start thinking not just about the number, but if to see if they can reduce the number and do whatever they want to do with fewer numbers. So maybe a satellite that has better safety constraints built into it can be charged less. A constellation that is not causing a lot of stress on the orbital environment will not have to pay a lot, but you charge a rent for the satellite operator that does cause a stress in terms of the number that they have, and things like this. So that's one of the ideas I had. Another is that you have this system because there is a technology moat in terms of the launch advantage and the satellite manufacturing advantage that a few countries have. I mean, China is doing it now increasingly, but America has already done it. The US has already done it with Starlink and a few other satellite mega constellations. How do you challenge this and make it fairer for other countries like India to also do it at the scale and at the pace that these major powers are doing it in? One of the ways is that you pull in a few different countries so that the technological maturation cycles are shorter, and you bring in a few competitive advantage, pull them in together. You can have one country manufacturing satellites and sensors, another working on launch, another providing a great spaceport to do all of this in, and you kind of create that ecosystem which can compete with the major superpowers, so that there is more equity in the system. We can also do open architectures in space so as to reduce the incentive for each satellite company to launch more satellites. The way right now it works is that all Starlink satellites are used only by Starlink and nobody else. But if you create some sort of open standards there, so that the satellites in orbit are an infrastructure that many people can use throughout the world, and the satellites are not proprietary technology that is used only by a few, and so you implement some standards in the inter-satellite links which make satellites talk to all the other satellites, and that can then provide service for everyone else. You remove the incentive for companies to outdo the other in terms of satellite numbers. So maybe that is one thing we can think about. That kills innovation, yes, but maybe you can think about it in terms of degrees of interoperability, where few things remain proprietary, but a few things are standardized. There is also the simple need to reform the ITU by a great deal. ITU right now is toothless. It is operating in a first come, first served system where it has no say in terms of implementing and voicing the concerns of all humanity around the world, the developing nations, the emerging startups. It has the mandate for equity, but no real power to actually act on it and implement it. So perhaps strengthening the ITU, allowing it to issue time-bound licenses that cannot be renewed automatically, and allowing some of these resources to come back to the global commons pool, which can then go to other countries and instead not have it locked up in perpetuity by a few major powers that have an incumbent advantage, is one way that we can think about this. And finally, the heart of the matter about the reason all of this occurs is because we don't have an authority above the countries that is able to think about these problems and solve them. But the reality now is that with so many assets in space, even countries like the US and China will start worrying about their assets, because like I said, if something goes wrong, if coordination stops, if there is a single bad actor who has little to lose and a lot to gain by any hostile activity, they can possibly disrupt the system for everybody. So it's not just that the emerging powers and aspirational space powers have an interest in preserving this domain for future use. It is also the existing major powers that already have a lot of stakes and a lot of skin in the game. So you cannot have a global governance initiative for space that suddenly you create a body and hand over your sovereignty over to it. But maybe we can start with clubs. Maybe a few major powers and countries like India, US, China, Japan, France get together and they decide on a few good practices that they are going to voluntarily follow. And that club gives each member certain advantages in terms of safety, in terms of communication, coordination. Like I said, it's a little bit of centralizing the coordination to make it safer. And if others want to join the club, they have to follow the rules. Then you're creating a bottom to top governance system that starts from the bottom and slowly goes to the top, where every country will eventually have to join the club if they're serious about space activities. And you have a model for governance there, instead of just creating an international body from the start and trying to make it work, which is unlikely to work in this domain.
Thanks. Oh, that's really fascinating, Ashwin. You've made the case for how this can happen, and the sense that we get is that without competition, it's unlikely to happen. So, I mean, the route to cooperation is actually through competition. So, by that, I mean international competition, especially between the US and China. It's also sobering to realize that India is not on the table. It's not going to be on the table unless it really changes the way it does this business. But there's certainly a pathway towards a governance of low Earth orbit. And it might require revising foundational space law. It might require a lot of cooperation between major powers that we haven't seen in the past. But it's probably the only way out. And I'm looking forward to more of your work on this. Please do check out Ashwin's paper on the subject. Nobody writes about it or thinks about it as deeply as he does. And he's also an engaging writer. So thanks again, Ashwin. I'm sure we'll be talking more about satellite internet again very soon.
Thanks, Aditya. It was a pleasure to discuss this with you.
If you liked our show, dive into Takshashila's research on technology, strategy, and economic affairs. Check us out at our Twitter handle @TakshashilaINST or our website takshashila.org.in.